Alright, so this is going to be the second lecture in the Macroeconomics 2 course. This course pretty much covers everything that we covered in Macroeconomics 1, but more advanced. So I'm going to do a Macro 1 course at some point as well, but I'm just doing this at the moment and it's more fresh in my mind. So that's why we're starting on lecture 2, because it goes over some more complex topics. I'll be recording lecture 1 fairly soon, but it's fairly self-explanatory. It just talks about growth in GDP and stuff about the Industrial Revolution, which is stuff that we've already talked about in our lessons when we were doing microeconomics, with stuff like the Malthusian trap and how we were able to escape from it. But anyway, we're just going to get straight into this because there's quite a bit of math in this one, which is why I chose to record the second lecture first, because it's easier when it's fresh on your mind. So let's get into it. The escape from the Malthusian trap. Economic growth has increased living standards throughout the world greatly since the Industrial Revolution facilitated an escape from the Malthusian trap, as technological innovation was able to outpace population growth, meaning that labourers were no longer required to live on subsistence wages. So, if you haven't saw the lesson where we talked about history's hockey stick and the escape from the Malthusian trap in Micro 1, the Malthusian trap is essentially a proposition put forth by the economist Thomas Malthus, and it essentially discussed the fact that every time we saw technological innovation in the past, so say better farming equipment leading to greater productivity, so we'd get higher yields of crops, although this would increase gross domestic product as we're able to produce more as a result of the technological innovation. All this would lead to would be population growth. So since population has grown, the product is going to, if we're thinking about how we calculate GDP, it's kind of GDP per capita, we take GDP and divide it by the population. So if the population grows, the GDP is going to be divided among more people, so they're going to have a lower GDP per capita. And this essentially means that as population grows, we see a return to subsistence wages. So be that as it may, it is clear that some countries have witnessed more economic growth than others. But why is this the case? Thinking about it abstractly, when we observe the long-run economic growth of a country with a growth rate of 1% and a country with a growth rate of 0.25%, the former country will clearly grow far quicker than the latter country. The Industrial Revolution saw so much increase in GDP per capita as technological innovation was able to outpace population growth that we describe it graphically as history's hockey stick. And that's the graph that we've got on the right. It essentially shows GDP per capita in countries, and we can see it's pretty much a straight line and very similar for most countries up until the Industrial Revolution around 1780 to early 1800s. And then we see a rapid increase in most countries, well, pretty much all countries, we see a rapid increase. And this is essentially showing how technological innovation has allowed GDP per capita to increase in spite of the fact that population growth has also increased in this period. Now, if we look at the fact that India and China are put much lower than Britain, Japan, and Italy on this graph, we describe this as the Great Divergence, as Britain, Japan, and Italy had much higher growth rates during the Industrial Revolution than China and India, although they're obviously catching up nowadays. And this is basically what we call the Great Divergence, and it shows how growth rates are able to compound growth, and countries with high growth rates are going to see far more growth in the same amount of time as countries with lower growth rates. So, how did the Malthusian trap operate? Prior to the Industrial Revolution, there were only brief escapes from the Malthusian trap, one of which occurred in 1348 following the Black Death. Since population declined massively, labour supply was less than labour demand, and therefore we saw a shift to the left in the labour supply and demand graph, and wages increased as businesses sought to entice workers from the limited pool that was left after the Black Death to work at their businesses. So the employers had to bid for labour, and since labour was limited, they had to offer higher wages to attract workers to come to their business than another business that was offering them more money. But then population increased again, leading to a turn to subsistence wages as the economy once again became a buyer's market in terms of labour. So the employers held the power rather than the employees. So that's something to think about. So economic growth is the growth of GDP per capita measured in percentage change over time. The mathematical way of showing economic growth is taking GDP per capita at the two time periods t and time period t plus 1 and putting them through the following equation. So this equation, the g basically just represents the constant growth rate. Now we can see the GDP per capita at time 2.1 subtracted by, then we subtract that by the initial GDP per capita and then put that over the initial GDP per capita. So this is a basic percentage change calculation. I'm sure you saw it many times before. And it gives us a decimal, and as you probably know, we just multiply that decimal by 100 to get it as a percentage growth rate. The y's are added to the formula to show that we're talking about GDP per capita at these time periods rather than just the time periods themselves. So GDP per capita at this time, let's say it's 2009, minus GDP per capita at this time, let's say it's 2008, over GDP per capita at 2008 again. So it's fairly simple. We can rearrange this equation to predict GDP per capita at a given time, presuming that the growth rate, G, is constant, which is represented by a line above the G. To predict GDP per capita at the time 2 plus 1, which is an arbitrary time feature in the future of t. So let's say again that this is talking about GDP per capita at time in 2009. So how are we going to calculate that? Well, we take GDP per capita at 2008 and multiply it by 1 plus the constant growth rate. And then that'll give us GDP per capita at 2009. That's another example there. Let's say, for example, we're given GDP per capita in the first quarter of 2022 as 11,000 at t, and the GDP per capita in the fourth quarter of 2022, let's say 2022, it's my fault, sorry, as £11,800, and let's say that's time t plus 1. and we are asked to find the growth rate, we'd put the numbers through the first formula and find the growth rate to be 7.27% to 2 decimal places. And if we were given this growth rate, we could plug it into the second equation to find the GDP per capita at time t plus 1. Make sure when you put g into the equation, you are using the decimal and not the percentage. And this is very important to remember, as when we're talking about other calculations later on in the lecture, we're going to be using the percentage. So that's when we're going to be going over the rule of 70 in a little minute. So this method can also be used to calculate population growth rates. So this equation here, where LT plus 1 represents, for instance, next year's population, LT represents this year's population, and N, with this line on top of it, represents the population's constant growth rate. So it's exactly the same as what we saw before when we said GDP per capita at 2009 is equals to GDP per capita in 2008. Multiplied by 1 plus the constant growth rate. But this time we're just talking about population. We can continue the process to calculate the population in 2 years. So instead of LT plus 1, it's LT plus 2 to represent its 2 years in the future. So let's say 2010. And that would be equal to the population in 2009, again multiplied by 1 plus the constant growth rate. So as we had before, population in 2009 is population in 2008 multiplied by 1 plus the constant growth rate. Population in 2010 is going to be the population in 2009 multiplied by 1 plus the constant growth rate. It's fairly simple once you wrap your head around it. But we can substitute the LT plus 1 with LT multiplied by 1 plus N, so the constant growth rate, since LT plus 1 is equal to LT multiplied by 1 plus N, which gives us LT plus 2. So population in 2010 is equal to the this. So it's basically just substituted, because we said earlier that this is the population in 2009 as we calculated it there. We've basically just substituted it, and this is the same as LT plus 2, so population in 2010 being equal to the initial population multiplied, so the initial population, like we said, in 2008, multiplied by 1 plus the constant growth rate to the power of 2. So, therefore, since each subsequent year follows this pattern, we can write a general equation of LT being the population size in a given year being equal to population size in the initial year multiplied by 1 plus the constant growth rate put to the power of the year we are looking at. So I hope that's fairly easy to understand. I hope it's been explained alright. If not, just put something in the comments and I'll go over it with you. So the general rule we gave for calculating population growth can be written plainly as the constant growth rule, which is something that you should take note of as it is important. And this is just like, it's the same thing we saw in the last slide there, just put plainly. So there is talking specifically about population, as we've said, LT is equal to population at a given time. We're just saying now that the variable at this time is equal to the variable at the initial time multiplied by 1 plus the constant growth rate put to the power of the time you're looking at. So we will now examine another rule that is important with regards to growth rates, and that is the rule of 70. This rule tells us that an economy, or anything, so any variable we're looking at, growing at a constant growth rate will double every 70 over the constant growth rate years. So population is going to double. How long will it take? Well, you just get 70 and you put that over the constant growth rate. So let's say the growth rate was 2%. You go 70 over 2 is equal to 35, so it's going to take 35 years for the population to double. So this rule shows us that countries with a higher countries with a higher growth rate will see their economy double in size in far fewer years than countries with a smaller growth rate. This partially explains the great divergence in size of economies since the Industrial Revolution that we discussed earlier. We can use the formula we examined earlier to prove this rule, but I believe it's fairly easy to understand in its most basic form that I've written there, as you don't really need to know how we derived it, but you derive it from this rule here. It's not necessary, but if any of you want to know how we got it, I have a sheet going that I got from the lecture saying how we did it. It's not necessary, but if you want to know, just put it in a comment and I'll do it in another video. So, we can use the formula we examined earlier to prove the rule, but it's fairly easy to understand as it is. I've said that. Note that for the rule of 70 equation, that the growth rate that we've got there should be given as a percentage and not a decimal. I think I mentioned that earlier. So a brief look at ratio scale graphs. With the knowledge of the rule of 70 that we just got, we can plot ratio scale graphs using the calculation, which are essentially line graphs with plots put at all of the years when population is expected to double, starting with the initial population, or whatever variable you're looking at the initial year. So let's say the initial thing in this time, a height, I don't know what this is, by the way, I just got it from Google Images, it's a ratio scale. So the height in meters at 3 seconds is 2. So how long is it going to take to double? It's going to take another 3 seconds to double to 4, another 3 seconds to double. This is not a very good ratio scale. I should have looked at this before, but it is not doubling as it should be. In a proper ratio scale, at every point it's going to double. So instead of those two are right, but then you'd expect it to have a plot at 12 seconds. You'd expect it to have a plot at 12 seconds for 8 and so on. So this variable would be doubling every whatever unit. Sorry about that, but it's fairly easy to understand anyway. We can rearrange our calculation used to calculate growth to calculate the growth rate. So the calculation here, we were calculating growth, so that's the initial thing, that's the thing in the future, so we're seeing how much that's growing based on the growth rate. Now we can rearrange that to find the growth rate. And to do that, we basically just put the at one point over the initial growth put to the power of 1 over the time at this point, and then subtract it by 1. And this nicely sums up all the aspects of calculating growth. Now, since the Great Divergence, many economies have converged, since rapidly industrializing countries such as China have extremely high growth rates, which allows their economy to double very quickly, as we saw with the Rule of 70 earlier. So, some final things to keep in mind are some important properties of growth rates. There's stuff that you can just know. I'm not going to say everything, you just take a look at it. It basically just means like this variable here, so let's say growth rate at z is going to equal growth rate at x minus growth rate of y if the variable is at x over y. It's fairly self-explanatory. I would go over it, but we're running quite long on time, so it's a lot of maths in this one. So finally, let's take a look at Cobb-Douglas production functions, which are the bane of my existence, but they are going to be coming into prominence in macroeconomics too, as well as a lot of prominence in microeconomics too, unfortunately. So if we look at the Cobb-Douglas production function here, so that's going to that basically represents production is equal to the level of technology multiplied by the stock of capital to the power of 1 over 3 multiplied by the amount of labour put to the power of 2 over 3. Noting that the 1 over 3 and 2 over 3 for the stock of capital and the amount of labour are based on empirical observations, as the share of labour in production in real life is approximately 66% relative to 33% contributed to production by capital. And we can rearrange this equation, which is the Cobb-Douglas production function, to calculate the growth rate of production as this representing the growth rate of the production function just being equal to the growth of the level of technology plus 1 over 3 multiplied by the growth of the stock of capital plus 2 over 3 times the growth of the level of labour. So that basic formula, if once you know what all the different parts of it mean, they are fairly easy to understand. It just looks scary when you're given something like that and you're given like YTG 80 and you don't know what any of it means, but we've just gone over it. And if you're given any questions on it anyway, they'll make it clear like what they're asking you. So if you're asked to calculate the growth rate of production, they'll give you the level of technology and the stock of capital and the amount of labour. So that's pretty much everything for the second lecture. So thank you.